a little bit late with this, but I got it done this morning. So I got the chapter 9 in-class problems on Blackboard this morning. And the format of these is just a little bit different, I think, than the other ones. So I've got the questions first and then some answers that follow. And I added another question and answer at the end. So that's on the Born-Haber cycle. So we're gonna talk about that today. We're gonna work that on Monday. There's a lot of, it's a very busy sort of problem to work, so I wanna look at it first today and then we can work it on Monday. All right, so before we, last time we were looking at this, and so the idea here was to have some sort of picture that represented enough of the information about electrons in atoms so that we could try and use that and predict what kind of compounds could form, okay? And so today what we're gonna do is look at that from a variety of different ways, and actually for the rest of this chapter and into the next chapter, we will be doing that with atoms and with molecules, okay? It's really important, but it's also not really difficult to be able to just look at the periodic table and know how many dots are in its dot structure, because you can't build molecules until you know that. So it's really, again, pretty straightforward. We're not gonna worry about the transition metals. In the case of transition metals, since we have more orbitals, we have d orbitals, the octet rule, or the 8 electron rule doesn't apply, since we have 10 d electrons. In transition metal chemistry, you use what's called the 18 electron rule. Okay, so we're not going to do that. If you take inorganic chemistry, it's sometimes we're going to deal with that. So we're going to stick with things that follow, for the most part, the 8 electron rule or the octet rule. We will look at exceptions, just like everything else in here. We have a set of rules, and then we have the other things that don't necessarily follow the rules. And so, again, it's really pretty straightforward to look at these things and see that everything in the column with lithium is going to have 1 dot, because that's 1 electron in an s orbital. And the beryllium column is 2, and so on, all the way over here. When we get to the end, at the noble gases, we have an octet of electrons. That's a special sort of stable situation. And when we look at forming ions, or when we look at trying to form covalent compounds, that's going to be the goal. That's going to be the target. If we can get an octet of electrons on atoms and molecules and ionic compounds and so on, then we're going to feel like we've done the right thing. Again, there will be exceptions, but that's the norm. So if we look at, well, suppose we didn't know, you do know, because we did this like in the first, week or 2 of class. Suppose we didn't know what would happen when I took some barium and some sulfur and I put them together, and I want to know what's the ionic compound that's going to form. Okay? So what we're going to do is sort of trudge through this from the point of view of electron configurations and an orbital diagram and with dot structures to see if we can predict what that would be. Now we know the barium is going to be +2 and the sulfur is going to be -2 and so on, but let's just pretend we never saw that before. Okay, so let's start with some electron configuration. So the electron configuration for barium is what? This is another thing. You should be good at this. It shouldn't take forever. So where's barium? Right here, right? Okay. So what's the noble gas we're going to use in big giant square brackets before that? If you go up a row, right? So we go here to xenon. Right. Okay. And then what? How many electrons does barium have in its valence orbital, and what's the valence orbital? So it's in row 1, 2, 3, 4, 5, 6. So it's going to be 6s2. Okay, so that's as an atom. Sulfur, let's see. Here's sulfur right here. So we're going to do that as neon in square brackets. And then what? Okay, so sulfur is going to be in this row, so in row 3, so 3s2. 3p what? 4. Okay. All right, so those are his atoms. Now, we have to know ahead of time that we're going to form an ionic compound here. So let's see if we can figure out what's going to be to sulfur's advantage when it tries to achieve in the ionic form an octet of electrons. Okay? other words, what's it need to do to fill up the S and the P orbitals? Well, it's 2 electrons short. So it probably wouldn't surprise us that sulfur would relatively easily accept 2 electrons. And if that becomes S2 minus, then that becomes 3p6. And then notice at that point that those are completely filled. Okay? So if we do that from an orbital diagram point of view, 3s, we had 2 electrons, 3p, 1, 2, 3, 4. That would be sulfur as an atom. And then, again, what does it need in order to fill the S and the P orbitals? Well, we need 2 more electrons. Okay? So, again, this would be S2 minus. If we do that from a dot point of view, what is the dot? Let's start with an S. How many dots are we going to put around sulfur? We do a dot structure. 6, right? Does it matter where we put the pairs? No. 3, 4. You can put 6 any way you want. The point is, how many are we missing? We're missing 2 if we want to make an octet. So I'll put those in. All electrons are the same, but we'll just pretend like the 2 we put in somehow are different. So no matter how you do this, from electron configuration to orbital diagram to dot structure, you predict sulfur is going to pick up 2 electrons and become S2 minus. Okay? It doesn't all have to be the same. You can't get different answers from different methods. Okay, so what's the deal with barium here? Well, what ion does barium form? +2, right? That's where it is on the periodic table. You know, it really has a couple options. The options aren't particularly good, but it has a couple options. If it could dump these 2 electrons, then it would have the noble gas configuration of xenon. So it could lose 2 electrons and do that. Or alternatively, it could pick up a whole bunch of electrons and completely fill, so barium's over here, it could completely fill all these d orbitals and the f orbitals and the p orbitals and pick up, I don't know, what, 10, 24, it could pick up about 30 electrons and I guess have a filled shell. That's not a good choice. Okay? So given a choice, it's always going to, every atom is going to pick the smallest change possible. So what barium's going to do is just get rid of these 2. Here comes barium 2 plus. If we look at that from a orbital diagram, then we just basically have all the electrons of xenon. Okay, so we don't need to draw all those out. If we do that from a dot structure point of view, barium starts off as an atom with 2 electrons. And again, I'm not going to argue whether they're paired or not. It doesn't matter. We're just counting electrons. What happens to it? And actually, here, I'll come back to that. What happens to it here? It's going to lose those 2 electrons, right? It becomes barium 2 plus. So when we draw something like that, what we're implying is that it lost the 2 electrons that would have been there. Okay. Now what's wrong with this? I told you I made a mistake here. What's wrong with this? When I put the 2 electrons there, I didn't change the charge. Okay. Once those electrons transfer, then we're done. The electron transfer happens in a very short distance. So those 2 things are right next to each other when that electron transfer process occurs. And then the cation and the anion stick together. And they're not coming apart very easily. We're going to look at this, how tightly those are held together here in a minute. So again, there's a variety of ways of looking at these. That's the same sort of scheme with lithium and chlorine. Those reactions, again, tend to be rather vigorous. We probably wouldn't do this without a lot of safety precautions. All right, so we're gonna come back to that. What we'd like to know is when I put these guys together, and when I go through this and I do the electron transfer and I put them together and they stick together, how tightly are they connected to each other? This is not really a bond. You'll get people that will argue that the ionic compounds don't have bonds, and that's really true, they don't. It's really an electrostatic interaction, so we can use Coulomb's law to predict how tightly or how that's what we're gonna work on. If I have a solid like this, we're gonna get energy out of it when we put them together. But that also means if we're gonna try and take them apart, we have to put energy in. So what we're going to do is we're gonna define something called the lattice energy. A crystalline solid is called the crystalline lattice, okay? So that's where the word lattice comes from. We're gonna define the lattice energy as the energy that's required to take 1 mole of an ionic solid and tear it apart and end up with gaseous ions, okay? And that's gonna really tell us how tightly those things are bound to each other. So in the case, since we've got barium sulfide there, we take barium sulfide as a solid, and we take it into barium 2+ gas phase, plus S 2- gas phase. The delta H for that reaction is what we call the lattice energy, okay? And it's usually very large. Would you expect it to be positive or negative? So this is delta H lattice. What do you think? If you can take 2 things with opposite charges and pull them apart, does that require energy, or do you get energy back? It's going to require energy. It's going to require a lot of energy. Okay, lattice energies are usually pretty big. So lattice energies are always positive. If that wasn't positive, then this probably wouldn't exist. If that wasn't positive, then the ions would be happier being separated. We know that they're not. Okay, so what we want to do, we're not going to calculate this directly. We're going to look at it in a couple ways. One, we're going to look at what are the characteristics of the cation and the anion that would cause this energy to be large or small. So we want to be able to look at compounds, ionic compounds, and be able to predict relative trends. Okay? Well, this really, again, goes back to Coulomb's law. I don't know what happened to these little question marks. Those are supposed to be proportionalities, like this one. We can look at these and say that, and look at what affects the energy between the cation and the anion. So if we follow Coulomb's law, the energy of the interaction is proportional to a couple of things. One, the product of the charges. Okay? So let me put another one up here. Let's do a sodium chloride. Sodium chloride solid goes to Na plus, gas plus, let's see, Cl minus, gas. Okay? So this would be the lattice energy for barium sulfide. This would be the lattice energy for sodium chloride. We have to suspect that these 2 lattice energies will not be the same. Because without even, you don't even need Coulomb's law to sort of intuitively expect that the +2 - 2 combination is going to be held together tighter than the +1 - 1 combination. And Coulomb's law verifies that. So the electrostatic energy, the energy to pull those guys apart, is proportional to the product of the charges. Okay? So what that means is, if I look at the numerator for sodium chloride, it's a +1 and -1, so it's a product is -1. For barium sulfide, the product is -4. So Coulomb's law would predict these 2 without any other differences. These 2 are held together with an energy or a force that's 4 times larger than these 2 because of the charges. But it's not always just the charges. The other thing that's important is the distance between the nuclei. And again, what we're going to do here is take the distance between the nuclei and partition it. Some of it belongs to the cation, some of it belongs to the anion. Okay, well, how much? Well, we know what those sizes are. Those have been measured. And if we look at that, then the distance between them is going to be the sum of the radius of the one plus the radius of the other. Which means we need to know the relative sizes of these things. That's why we did the size stuff before. So, when we try and look at trends in electrostatic energies, we have to take into account the charges, and we have to take into account the sizes. And we'll look at some numbers here in a minute, but just as a general rule, the size does matter, but the charge matters a lot more. So if you have changes in charges and changes in sizes, then the change in the charge usually overwhelms everything else. And again, that's because it's a product of the charges, and here you're just looking at the sum of the sizes. Okay? So let's look at some data, and then what we haven't really done here is say, well, how do we measure this? That's what the Born-Haber cycle does, so we'll come back and look at that, but let's get the concept under control here. That's what we just said. Let's look at some data, okay? So this is lattice energy over here, so that's the energy to pull them apart. And notice we're doing more than just pull them apart. We're taking the solid and we're pulling it apart, and we're putting these in the gas phase, okay? So it's pulling them apart and vaporizing them. That's one of the reasons the energies are generally pretty high. So this is the lattice energy, and then on this axis, we have the various halogens, okay? So fluoride, chloride, bromide, and iodine. And each line here represents the interaction of an alkali metal with one of these. And each dot represents a lattice energy, okay? So let's look at column here. So this guy right here is the lattice energy for lithium fluoride. Again, we don't really care about the number. What we're gonna care about is how that number compares to the other ones. So if we stay in this column, all the anions are fluoride. But what changes is the cation, okay? So if we look at this, this is the lattice energy for lithium fluoride. This is the lattice energy, so 900, whatever units, we don't care, units, is the lattice energy for sodium fluoride. So the sodium fluoride lattice energy is less than lithium fluoride. And notice if we keep going down here, as the size of the cation gets larger, the size of the lattice energy goes down. Okay? So what did Coulomb's law predict? Well, in that sequence of events there, the cation charge and the anion charge was always the same. They were always +1, -1 combination. Since we kept the fluoride the same, even the anion radius was the same for that series. The only thing that was different was the size of the cation. As the cation got bigger, the data said that the energy was smaller. Well, where is that value right here? That value is in the denominator. As the denominator gets bigger, then the fraction gets smaller. Okay, so the energy is inversely proportional to the distance between them. If you look at every other combination that's on here, it follows the same trend. Now, the increments aren't always equal. There's a pretty big jump between lithium and sodium, and there's a smaller jump between potassium and rubidium. But still, it follows that trend. Okay? Let's look and see what happens if we keep the cation the same, but now we modify and change the anion. That should follow the same trend. So let's take potassium here. So this is potassium fluoride, potassium chloride, potassium bromide, potassium iodide. Notice as the size of the anion gets larger, the lattice energy goes down. Okay? And again, Coulomb's law would predict that. And so, again, if all the charges are always the same, then it's relatively easy to look at the trends in these things because you just compare the relative sizes. If the size of the cation and the anion gets larger, you're comparing that to a smaller combination, then it's really easy. Okay? That's certainly going to be less. So the general rule is the smaller the cation, the smaller the anion, the higher the lattice energy. And again, that's just primarily a function of the distance between them. Okay, what happens when we compare charges? We're going to look at that in a little different way here in a minute, but we should be able to figure this out. If we wanted to compare the relative lattice energies of barium sulfide versus sodium chloride, okay, we have two things that are different there. We have charge differences and we have size differences. Barium sulfide barium is larger than sodium. Sulfur is larger than chlorine. So if we just ignore the charge part of this, and we really can't, if we ignored the charge part of this, which one of these two would we predict would have the lower lattice energy? Even one that has the biggest species, right? If we look at the experimental data, what we find is
is this lattice energy is much larger than this one. And it's much larger because in that first comparison we made, we ignored the charge. So the fact that we have charges here that are +2, -2 means that, to a first approximation, the electrostatic interaction here is 4 times larger than it is here. So again, typically charge will sort of overwhelm any differences in sizes. And we'll look at a couple examples of that in a minute. Okay, so then we ask, or we could ask, well, how in the world would we measure this? Everybody would want to measure lattice energy. I mean, that's a fun weekend activity. If you think about this process, where are you going to get a device to do that? You can't open a catalog and say, I'm going to buy the latest. You can't go to Amazon and buy a lattice energy measurer. It's a pretty tricky process. You're going to take something that's a solid and turn it into ions in the gas phase, and somehow you're going to measure the energy associated with that? Okay, that's not a single measurement that's made. In the thermo chapter, we talked about energies and tables of values that came about because people had calculated those based upon other known thermodynamic data. And this is clearly one of those. So anytime you can't measure something directly, you try and use existing data to calculate it. Sometimes that's a simple process. So again, when we did the thermo chapter, we looked at adding 2 or 3 equations and you get a net equation and do the same thing to delta H's. Sometimes it's a little more complicated than that. This one's a little more complicated. So this is called the Born-Haber cycle. The idea here is to be able to calculate the lattice energy, okay? So if you look at this, there's a lot of stuff going on here, but every one of these steps is something we've seen already. So here, this right here, this is for lithium fluoride. So from lithium ions combining with fluoride ions to give us lithium fluoride, this enthalpy change is the negative of the lattice energy. Why is that the negative of the lattice energy? So if we have these reactants going to this product, that's defined up here as the negative of the lattice energy. Well, we define the lattice energy as the energy to take it apart, right? So this going from the ions to the solid is just the opposite direction. So in the opposite direction, you just change the sign. Has anybody seen this before where lattice energy is defined in the opposite direction? Please tell me no. Okay, good. There are some books that do define, the book we use for inorganic chemistry defines lattice energy in the other direction. And that's a nightmare to try and straighten that out. So if you've never seen this before, then you're not biased that way. All right, so that's the number we want. We'd like to find that. The nice thing about delta H, remember delta H is a state function. What that means is it doesn't matter how we get there. We could start someplace and end up someplace and follow one pathway, and the sum of all those steps is equal to the delta H for a different pathway. So we're interested in this, but there's no experimental way for us to get there. So what we're going to do is take a different path. We can look up various values. Okay, so the scheme here is to follow this pathway over here. We're going to go around here and follow this, and then we're going to use that to calculate this. Okay, so today, again, what we're going to do here now is describe it, then on Monday we'll do the problem that's in the in-class problems. So what do we know already that we've seen before that we could use to sort of go around the path to get this one? Well, we know if this is lithium fluoride solid, we've already talked about the delta H of formation. Maybe we could use that. Okay? So remember, the delta H of formation is the enthalpy to make this form its elements as standard states. So if we take lithium solid and a half of a fluorine molecule, that would be the elements of standard states to make lithium fluoride. If we knew that delta H, we'd be started. Okay? And we do. You can look that up in tables. Delta H of formation is well known for this. What we ultimately want to get to then, since we've got these apart, is we want to get to lithium being a cation and fluoride being an anion. Okay? Well, what do we have to do? We have to go through that stepwise. So each one of these steps corresponds